A little bit about myself. I am a postdoc at the National Center for Atmospheric Research, and I have been there for about a year. I did my PhD here at UW in civil engineering. So I had another life before I was a graduate student. I was a design engineer. I designed pipes and pumps, and I didn't like it very much, so I went to grad school and ended up studying computational hydrology and did a bunch of climate modeling from inside a civil engineering department. So I ran a high-resolution regional climate model for my dissertation work. The study domain was in the Arctic, and we produced lots and lots of data from this climate model, and I didn't have tools that I liked to work with that data that the model produced. And so I ended up working on this Python project called Xray. It's an open source package. That's most of what I'm going to talk to you about today. Does everyone have this Jupyter notebook open? Is anyone having trouble finding it? The kernel that you want to use is the ND Arrays kernel. That should be available to all of you as well. So we'll just jump into it. I have two notebooks. The first one is got lots of words and is pretty high level. This is how you use these packages. The second one has less words and does some science-y stuff and is kind of meant to let you play around with a little bit. So it's a test drive of Xray later on. But so we have some real data we're going to play with today. We have some reanalysis data from Era Interim, and it's you can download it from ECMWF. We've already put it on the Jupyter Hub in a place that's accessible here from Jupyter Hub, so you won't have to worry about that. But we have some air temperature and some wind and some sea surface temperature data sitting in this path up here. So make sure to run this first cell. That'll kind of tell the rest of the notebook where to find the data later on. And I'll just kind of scroll through this and talk a little bit about some background. Feel free, if you're wanting to move ahead a little bit, you're welcome to. Feel free to change all the cells. We're going to break stuff, and that'll be part of the fun here today. So I wrote a little open tutorial data function here that we'll use kind of over and over again, but it's just a way so that we can get some data into the notebook. So go ahead and run that, and then we'll just open a little bit of Alaska data. So what are multidimensional arrays? Actually, before we go there, can I get a raise of hands if you've used the package Xray before? Sweet. Okay, this is good. This is good. So there's 8 of you, and then the rest of you, this is going to be new stuff. It's great. How many of you that didn't raise your hands have heard of Netcdf files? All right, so most of you. So the easiest way for me to describe the Xray data model is that it's built to emulate the Netcdf data model. Okay, so here in this first section, Introduction to Multidimensional Arrays, there's this image that has some data cubes in it. And you might think of this as a Netcdf file. It can have multiple variables in it, temperature, precipitation, and it might have some coordinate variables that describe the locations of grid cells in these arrays. So latitude and longitude. You might also have a time coordinate as well. So just as a kind of a point of order, nothing I'm going to show you here today is outside of the realm of possibility without Xray or without Pandas. You can do all this with NumPy, or for that matter, you can do all of this probably with Python built-in lists. All right, but everything I'm going to show you today will make your life much, much better and more productive and happier, and you'll get more vacation time and all of those things. So, and the reason for that is we're going to work with labeled arrays. So if you've used Pandas before, you might understand what it means to be a labeled array. Like you have an index that is paired with the data that you're working with. So rather than say I want the 4th index position in a time series, you might say you want the data from like June 3rd, 2017. Okay, so that's a lot more descriptive, and maybe it raises an error if you do something wrong, whereas if you do that with NumPy, it's just going to give you the 4th position. So Pandas is really a precursor to Xray, and Xray is really built on top of Pandas. It uses a lot of the same concepts. But Pandas only does tabular data. So we saw Pandas as part of GeoPandas a few days ago. Make sure to keep running these cells as we go too. I'm going to forget that if I just keep talking. So there's a cell here that I'm just going to print some a NumPy array, but as you see here, there's no labels associated with this. This is just a grid of numbers, and you can index into it and do things like that. Okay. Pandas is, we're going to get a few warnings, but Pandas is a tabular data structure. It's got a bunch of tools built onto that data structure that allow you to do fast tabular data manipulation. But at its core, it's tabular. It's going to do, think of it as like an Excel sort of format. You have 2 dimensions at most. So here I just used Pandas to open up a table from NASA that has the global average temperature for each year, going back to, actually I don't know how far it goes back. We'll have to look. So if going back to 1880, okay, so they have some way of estimating the global average temperature, and I parse this text file off the internet and we get a little table. So this is what a Pandas data frame looks like. We have an index, year, and then there's 2 columns. In this case, the 1-year and 5-year averages. And like I showed, like I have here, you can just select 1984 through present, or maybe I just want to do the 1980s. Okay, and so I get the 10 years in the 1980s. Built into Pandas is some matplotlib convenience plotting. So I just press data frame plot, and it's going to plot both of those variables for me. So that's a little bit easier than creating the figure yourself and then making line plots and adding the time variable. Pandas is going to say, oh, I see an index here. I'm going to just put that on the x-axis for you. And oh, there's 2 variables. I'll go ahead and add a legend for you. So as you can see, it's getting warmer. I don't know if you guys have heard. It's getting warmer here on Earth. So there you go. Okay, so I mentioned a second ago Netcdf. So it's the network common data form. Some people got together and said, we need to store binary data, and let's not just do it as binary blobs on a disk. Let's come up with some standard of how to store these binary blobs with some metadata so that when I give you my data, it means something to you. And I don't have to tell you over the phone that it's 4-byte integers stored in this particular way. So. And it's pretty widely used. Most of you had heard of it. Many of you have used it. A lot of climate models use it, but you can get observation data in Netcdf form or that sort of thing. So, and as of Netcdf 4, these files can be really big. We can have tens, hundreds of gigabyte files. And that means there's an array sitting on disk that is really, really large. So part of what Xray is trying to do is provide tools that allow you to work with really large data sets that are labeled, that have these coordinates that go along with these big data sets. So there's a bunch of text here on what is Xray and when to use it. I think you should always use it. If you're using array data that can be stored as arrays, so not vector data, basically, but if you're using something that kind of sits on a grid, Xray might be a very nice choice. There's 2 basic objects in the Xray data model. There's a data array, which is a variable. It's a single variable. So in this, coming back to this figure again, temperature would be represented as a data array. So it's homogeneous in type. So it's all, say, floating point numbers, and it's all temperature. Precipitation would be another one. And then there's a data set, and this whole figure is a data set, or could be a data set. Okay, so precipitation, you might have a mask that's Boolean in there. So you can have different types inside of a data set. A data set is a dictionary or a collection of data arrays. And inside that data set, they can share coordinates. So they all can have the same time dimension, but you can have temperature and air temperature and sea surface temperature and U and V winds and all of that. So we can go ahead and keep running through the notebook here. One of the nicest things for those of you who work with, read files off the disk all the time is Xray supports a bunch of different backends, which means we can read Netcdf files that are formatted in Netcdf 3 format or Netcdf 4. We can read grib files. We can read we can read HDF5 files in some cases. So a lot of what the geoscience community has done, we can do rasterio. We can read raster files into Xray now. So geotiffs or whatever rasterio supports as a backend, Xray will also support. So this makes it really easy to get your data from some file into a labeled data array or data set pretty easily. So here we're just going to load this air temperatures. This is global air temperature. It's daily. This is, we can see how large this is. So you can always, NBYT, did I spell that wrong? So this is in gigabytes. Let's see here. By the way, there's a little bit of a chance that we're going to break the machine that we're running all this on. So like it's not doing anything for me right now. Oh yeah, okay, so this is a 12 gigabyte data set. Xray is, we can't all load a 12 gigabyte data set into memory on this machine, I don't think. We could get close, but not quite there. Is that working, or do you want to just be able to?
Your audio, I think the battery might have died.
On which one? On the room one? All right. Oh yeah, it's dead. All right, let's see. Oops. Now I'm going to get all tangled up. Here you go. Cool. So no one could hear me, which must have been nice. All right, you can hear me now? All right. So one thing that Xray does is it is lazy. And what I mean by lazy is it's not going to take data off the disk until you actually use it. So I can open the data set, but the data is still sitting there mapped as an array on disk. And then when I want it, I can load it in all at once, or I can load in chunks of it at a time. We'll get to some of that. So this data set is 12 gigabytes of air temperature data, and we can look at what that data set looks like. It has, by just printing it here, you have 3 coordinates, longitude, latitude, and time. You can see the size of these dimensions. So we have 241 points along the latitude dimension, 480 along longitude, and then 13,000 along the time dimension. So this is a pretty sizable little data cube that we have here. And each of these variables may have some attributes and metadata that sits along with them. We can just take the air temperature data array outside of the data set by grabbing it just like it was a dictionary. And what we'll start with is looking at some indexing. There's a bunch of different ways you can do indexing in Xray. The first would be you can index it into this data array just like you would in NumPy. So this is positional indexing. You just go ahead and grab a slice of data. Here I grab the first element out of along each dimension. And I get a single data point. So at that point, on that day, or on this point, on January 1, 1979, it was 241.95 degrees Kelvin. Now, so if you're just going to use Xray like this, I'd say just stick with NumPy because you're not getting a whole lot out of it. But now we can start playing around with label-based. So here I'm going to use the loc method, and I'm just going to say, give me 1979-01. And so this is going to return a 2D array. I don't need to know which dimension, which positional dimension the time dimension's on. Xray is going to handle that for me. Even better, I can say, I can use key value pairs. So the iCell method is going to do positional indexing, but I'm going to tell it which dimension to grab each of these from. So here I'll grab, this is going to give me the same data that the first one did, but now I was a lot more explicit about where to get that data from. Of course, we can do better than that. We can use the cell method instead of iCell, and the cell method is actually going to use the values that are stored in those coordinates. So we're going to do a lookup in those coordinates for the closest point to 75.0, 180.0, and on that January 1st, 1979. So here we'll get that same, this is a new point. Now we're at latitude 75. So that's how to do indexing. We can kind of move quickly through here. There's a challenge here. If you want to come back to it, you can actually select slices. So if you know what the slice built in Python is, you can set ranges using slice. So I can select a slice of latitudes using the cell or iCell method. We just have some nice plotting utilities, just like in Pandas, except now instead of just being tabular, we can do multidimensional data. So here's a time series I'll select for 5 days, and make sure you have your matplotlib inline magic run here. But this is a time series. So I just selected for a range of days, and then for 1 point. It's getting warmer there too, probably because it's spring. You can modify these. These are just matplotlib plots. So you don't have to learn a new plotting library. We're just wrapping matplotlib in Xray. So here I'm just going to select 1 day, and we're going to make a map. This is really combining a lot from what the last session did. So here's the temperature over the full model domain for 1 day. You can see the continents, and this is air temperature, which is kind of fun. You still can see the continents there. Building on top of what we just did, so we're just continuing to go through. We can add some information to this figure. So I added some titles and that sort of thing. And we can use Cartopy to do projections. So if you thought Cartopy was easy by itself, try this out. Because now it's going to automatically look in and say, oh, you have longitude and latitude coordinates. I'll use those. And you don't have to keep those coordinate variables separate. And so here, we just made a little orthographic projection using that same data. We went ahead and changed the color map. Pretty cool. Questions? Plotting? Indexing? Data selection? Yeah?
So you said also you can do H5, which is probably the same thing depending on the Netcdf.
Yeah.
So when you read in like the Netcdf, can you also do this? You said H5 unlimited.
I don't know what you mean by that.
Well, I'm just saying that you said we can do H5. But
Yeah. Okay. So you can do a subset of H5 files. So if they're formatted in a certain way, there's some people actually working right now on like a wide open H5Py backend, so that you could kind of go wild with it. But right now, they kind of have to look like a Netcdf file.
Okay.
So, but probably within a year, we'll have kind of like a full HDF5 backend. Are you an HDF5 user?
Yeah, we're currently setting up Python H8 with H5.
Sure. Yeah, well, we can talk about it more. I can kind of point you to the progress that's being made there. All right, so these variables, of course, we don't just usually want to select a slice and make a plot. We like to do math on them. So here's the difference between 2 days. This is January 1st, the difference between 2 January 1st. Yeah?
Sorry, before the plot, Cartopy plotting.
Yep.
The math data.plot statement, given that the Netcdf file is so much built-in metadata, as you pointed out.
Yep.
You still have to, here you're still passing the outside knowledge of what projection did that it's plot correct to the transform. is there any way to read directly from the Netcdf file and pass it to the transfer parameter?
Yeah, so if you,
That's as easy as that.
yeah, so if you want to put that metadata in your Netcdf file, go for it. But it doesn't always exist there. So, and then you could, you could have a little helper method that does something like that. But something that Xray has done, if you are familiar with some of the other kind of labeled array packages that the climate community has used, Xray has tried to kind of stay out of the business of being domain specific. So it's Xray, has the largest following probably or usership in the climate and geoscience community, but there's a pretty large chunk of people using it in the finance world as well, and kind of everything in between. So if we start saying that everything has to have units of Kelvin, then we're going to lose that user community. And it's going to kind of be a pain, because if your data has units of Fahrenheit for some reason, then you always have to kind of work with that. So this doesn't do everything for you. Cole wants to know if I'm on campus today. I am. Get out of here. All right. So, but yeah, that's a good question. So we're going to make this plot again, just make sure we're in the right spot. So here's the difference between 2 days. We can do more, I'm gonna go ahead and delete this, that doesn't need to be there. So we can do, use ufuncs. Xray supports NumPy ufuncs pretty extensively. So here I'm calculating the wind speed as the square, the sum of the square of the u and v components. And we can plot that. And we plot, this case, with the quiver method, so you get the little arrows that kind of scale with the magnitude and the direction of the vector. Let's see, so here we're just going to select one particular June, July, August. So this is 1979 summer months, basically. And I can take the mean. And notice I'm taking the mean here along the time dimension. I don't say take it along the 0 axis, take it along the time dimension. So if your data's, this makes it really easy to kind of move between data sets and continue the same sort of analysis workflow. So get the same, this is the June, July, August temperature mean. Here's another challenge for you if you want to calculate the maximum air temperature during that period, and then make a plot. You can come back to that. One of the things that people love about the Pandas data frame, which also exists in R, and it's not a new concept, but is the group by functionality, where you can select groups of data along your index and then operate on those groups independently. So here I'm going to take the group by time. Let's actually do group by time.month. Oops. All right. So this creates a group by object. And now all that has really done is kind of decide which data goes in which group. But then I can calculate the mean. There's a bunch of ways you can do this. We can use the apply function. So I can apply an arbitrary function to each group. So it's chunking here, it's working. Let's see if this might be the time we break the computer. I haven't gotten to the out of core piece yet, where we'll definitely break the computer. So what it's doing right now is it's split this data array up by individual, the months of the year. So there's 12 different groups, and it's calculating the mean. Oh, and it's going to make, okay, yeah, there you go. So we calculated the monthly, a bunch of monthly means there. This would do the same thing, so I won't run that, but you can if you want. So you can group by season, and then take the difference here. So this is the range between the winter and summer seasons. This is just kind of showing you some of the functionality you can get out of this. And there's a lot more. You want to take rolling or moving window, apply rolling or moving window functions to Xray objects. You can do that. You can resample. So if you want to resample along the time dimension, say go from hourly to monthly data, you can do that. And I'll leave some of those things to you guys. But while we're waiting for these plots to make, oh, they're here now, but I'll say the Xray documentation, it has a lot more examples than I can go through in an hour. So I'm breezing through some of this, but if you say, hey, I think that would be a really useful thing, we might already have it and it's sitting in the documentation. So I have probably 2 more sections that I really want to get to, and then we'll see if we have time for the advanced tutorial or let you guys play with that at least. So something that we've been working on is allowing out-of-core computation. So everything we've done so far has used a single process to operate on the data. We read the data with one process and we operate on that data with the same. But sometimes we work on data sets that don't fit in memory. I work on a supercomputer where my interactive nodes have 1 terabyte of memory, and I can run out of that. You know, depending on how big of the data set you're working on, you'll always find a way to run out of memory. So out-of-core computation means, what if I actually just work on pieces of this, my data, in a way that's in parallel? Maybe I can utilize all the 16 or 32 cores on my machine and not run out of memory, leave some on disk when I'm not using it, and then just keep the parts that I need. So there's a library called Dask. Who's heard of Dask? That table, and a couple people from that table. So Dask is a library that is a task scheduler and optimized parallel processing backend for things like NumPy and Pandas. It has a number of collections. You can see here, if you're interested in kind of like making your data processing kind of scale out beyond a single core, Dask might be something to look at. And what it does is it basically looks at your computation stream and says, these are a series of tasks you have to do, but I don't have to do them all as soon as you ask me to. I'll wait until you need the final result. And by doing that, it can optimize what computations it does and what maybe it leaves some out, and then it can select an order that is going to be more optimal for actually getting your pipeline finished. So you see this little animation. Basically, we're taking a bunch of chunks of data and we're doing some reductions to them. And at the end, all of these little red boxes will turn blue, and the bottom one will have a final array. So it's just an example of if you had an array that you could split into smaller chunks, then you can kind of let each chunk go asynchronously. So let's go ahead and open up a new data set. It's actually the same data. This is going to have 4 variables in it now. So there's and let's see how big that is. It's probably pretty big, right? So this is 50 gigabytes. So if all of us 40 people open up 50 gigabyte data at the same time, I don't know, it's hundreds of gigabytes, 2 terabytes. So we won't do that. But what we did is we passed in this chunks parameter. Okay, and so if you say ds.chunks, it's going to tell you that it has this data set chunked along the time dimension in 1,000 element increments. Okay, so we've got a bunch of chunks here, and that's good because we're gonna execute this the first time in the wave. Like I'll kind of like have this side of the room do it, and then the middle, and then the right side, just so we see how it goes. So you can go ahead and execute this kind of like from business here. We're going to get some diagnostics in a fancy plot from Bokeh. You guys didn't cover that in the visualization, but it's kind of a fun plotting library. So I just calculated the seasonal mean of this 50 gigabyte data set. I guess I did just select sea surface temperature only. So it's slightly smaller, but it didn't do anything. You saw that finished immediately. And the reason is because Dask is just building its task graph when it's doing that. And I'm pretty sure this is not going to work for you guys. And so yeah, no dot graph for you. For some reason, graph viz is not working on the Jupyter Hub right now, but this would allow us to plot something that looks like this, make our task graph. And it looks much more complicated than this. There's a bunch of like slicing and stuff where it has to reach around and grab things. So, but now we can go ahead and compute this. So the compute method in Dask will actually tell it to do its thing. All right, so let's see the left side. These two tables will give you guys like a 10-second head start. And then I'll just, oops. Guys, new terminal. We'll just watch along here. All right, so what you're seeing if you're looking at top here is that the CPU usage on each of these processes is more than 100%. All right, so there's some threading going on. So it's reading data off the disk and it's splitting it out. So I said, I skipped past it, but I limited how many tasks you guys could do at a time to 4. So that we only can do as much as 160 in the room at once. But you're seeing that we're actually threading, operating on these arrays using threading. Okay, so 215 CPU, something like that. Go ahead if, so mine's done. So I can visualize this and I can see how this operated. So let me know if this doesn't work for anybody. I see it on some people's screens, so it's working. So this is saying that I let it work on with 4 workers, and it did some things. So here it was getting the data off the disk, and then it's taking the mean of each of those 4 seasonal chunks. So this is just for one set of one set of the time data, and then eventually it's going to bring all that together. So it has some tasks to do here at the end where it's taking the mean of other chunks and bringing it all together. And you can see we had CPU that got up to about 200%. I'm not exactly sure why we don't get to 400%. And the architecture of this machine is new to me. So. But we got to 200% CPU at times when we were doing a lot of compute, and then sometimes we just had to read, and the disk was kind of slow, and so it wasn't quite as high. So you can do some diagnostics on the Dask stuff, but we just chunk through a few tens of gigabytes, all of us at the same time. You guys can do it if you didn't do it already. So that's Dask. So we just did. We're running Dask right now on a single node, one computer that has multiple processors. It's also possible using Dask distributed, it's another parallelization backend, to run on multiple nodes. And I'm not going to cover that today, but I do have a link in the advanced tutorial on kind of how we're setting that up on some supercomputers at NCAR, if that's something that you want to try. So the theory is we can do what I just did here on 10 gigabytes on 10 terabytes or a petabyte, or something like that, if you give it enough nodes to work on. So, anybody have questions about Dask? I know it's kind of a new concept for some. Cool. I will say the big caveat that I have to throw in is that it doesn't always work like you want it to. Like you can do things, parallel computing. Like you can do things that make your program slower because you tried to parallelize it. So if one process has to wait for a while, if you chunk along the wrong dimension, it's going to spend a lot of time kind of like moving data around and not a lot of time doing computations. So it's just something to think about. It's not like totally seamless. Like you just press chunks equals 1,000 and magically your code goes 16 times faster. Wouldn't that be nice? Okay. So the last thing here is there's some masking functionality. A lot of times what we do is we have this big global data set from a climate model and we just want to select the parts over some region. So there's a bunch of different ways you can do that. The where method is probably the best one right now. Whoa, don't do that. Sorry, I'm losing it. So here we're just going to select all the data that is above 293 degrees Fahrenheit, or not Fahrenheit, Kelvin, that other unit. So here is just, and we basically just selected the tropics and mid-latitudes. All right, and this is just air temperature. So, of course, we can just take the first time point of the sea surface temperature here. And what we can do now is we can say, okay, we just want to select, we can basically build a mask in here where we're going to have land being 1s and ocean being 2s. So you can use the is null over the sea surface temperatures. And if the data is null, which it will be over land because there's not a lot of sea surface there, it'll be true. And then we can use that to mask our data here. So what I just built is a mask that is 1 over land and 2 over ocean. And then we can add that to our data set. And where's the where? Oh yeah, here we go. So now we're just going to plot is this the ocean? What was 1? Land. Just data over land, and we'll take the mean along the whole time dimension. So we're still using Dask here, and instead of using the Bokeh interactive GUI sort of diagnostics, we'll just do the progress bar. So you'll see this progress bar start chunking along. And look at us go. Woo! We're all doing all the math. All right, let's see. Oh, we still got a little bit of time. We're going to get into the advanced tutorial. Cool. Some of you are getting more than 200% CPU. That's pretty neat. So it's got a couple tasks, and I think it gives 1 line for each task, right? The first one is take the mean, and then it has to do a where. So there's some broadcasting it's doing, and it's just zooming along. All right, I think you all can run it. We're not getting too close. We still have 40 processor equivalents sitting empty. Great, it's working. We're not running out of memory. So one of the nicest things Dask does is operates lazily and then throws away the memory after it's done. So you'll use 1 chunk of memory and then it frees that. And so you can really work on a data set that's terabytes large in the same way. Yes?
I have a really simple question. So if you're looking at the legend and you're like, what are those values? What is SST? You can go back and say yes and print out all the variables.
Yep.
But is there more metadata somewhere?
Yeah, okay. Yes, so if you do ds.info, those of you who know Netcdf, NC dump, this will be familiar. So here's the rest of the metadata. Some data sets have like tons and tons of metadata, and if you printed it out every time, you'd never be able to find what you were looking for. So we kind of limit it a little bit. But yeah, ds.info, Ethan let's talk to. So that's a good question. So there's lots more you can do with masking. There's some good examples out there of how to mask with shapefiles. So you can use GeoPandas and Xray together to mask a gridded, say, climate model to some shapefile domain. So you can do stuff like that. So at the bottom of this notebook here, there's a ready for more, head to ND Arrays Advanced. We can go there. If anyone has questions while we click on that button, now's the time before we get into the advanced section. You can never go back.
So how hard is it guys to do actually set up in parallel?
So the setup is easy. I mean, installing it is a conda install Dask, and then the jump from using Xray's array backend of NumPy into the array backend of Dask is as simple as adding that chunks keyword when you open the data set, or the chunk method if you are creating it some other way. How easy is it to get like the best performance out of it? It really depends on what you're doing. So I picked some examples that I knew I'd get some improved performance on, but if you're working from a lot of, so here's an example of what won't work. If you have, say, 100 files that Xray is gonna kind of concatenate for you, and then you're gonna read chunks kind of along that concatenation dimension, you're gonna end up with like chunks that sit on like a bunch of different files, and it's gonna spend more time asking the computer where those arrays are than it is doing any math for you. So there's lots of ways to make it not work, but there's a lot of easy ways when it's like, yeah, this is definitely a really good, easy way to go. So, and every once in a while you can, Dask is its own library. Like you can go deeper than what Xray exposes. So there's ways to optimize if you really want to go. So, okay, I have this advanced tutorial that you can just run the whole thing if you want. or we can go through it. But there's some challenges at the end and a link here on how to get Dask distributed up and going. There's two kind of examples here. So there's a bunch of packages that have been built on top of Xray. So one example is a package called EOFs that does imperial orthogonal functions on some sea surface temperature data to calculate the El Nino, the ENSO 3.4 index. So we can do that, and that's just kind of a way to show you that we can do some science out of this. And then there's another one where we use this region mask, which is a package built on Xray that allows us to do some masking and calculate the trends of temperature, global air temperature by different regions. So what I think we'll do is, I usually get lost when people tell me just talk through these tutorials. And so I want you guys to just like go play around, try changing the region, do the imperial orthogonal function on the Atlantic instead of the Pacific, see if that gives you anything interesting. You can maybe try to make some better figures out of the trends section. So, and then, yeah, if you are interested in kind of any more of the Dask stuff, I'm kind of in that mode right now, so I'd be happy to talk more about that off to the side. So I think with that, we'll just kind of like let you play with the tutorials, and you can ask me questions. I'll walk around.